For most of human history, survival meant scavenging. Early civilizations built their societies entirely around the raw materials they could pull directly from the earth, the forests, and the water. But relying exclusively on untreated nature comes with strict physical limits. Wood eventually rots. Untreated stones splinters and cracks under pressure. Natural pigments derived from plants fade quickly in the sun. As societies expanded, they needed materials that could withstand immense weight, dyes that could hold their color, and medicines potent enough to cure specific diseases. None of these existed in a readily available natural state. Humans were limited by a specific rule of existence. Matter was fixed. If a rock was brittle, it stayed brittle. You could search for a better rock, but you could never give it a property it didn't already possess.
More than 1,000 years ago, an 8th century scholar named Jabir ibn Hayyan inspected those raw materials and asked a different question. Instead of scavenging for what nature had already made, he wondered if we could force nature to yield entirely new substances. Jabir hypothesized that the physical world was fluid. Through careful, deliberate experimentation, he believed a material could be stripped of its original limitations and transformed into something else. This move toward active creation established the foundation for modern chemistry and manufacturing. To test his theories, Jabir built a laboratory designed specifically to eliminate environmental variables. It was a space where temperature, pressure, and time could be meticulously controlled. He brought in a wide variety of starting inputs: basic minerals chipped from caves, unrefined metal ores, and common chemical salts. Scholars of his day typically cataloged these items by their weight and color. Jabir treated them as ingredients. He subjected these ingredients to extreme heat, mixing, dissolving, and refining them. By placing them under controlled conditions, he created a specific reaction zone. Here, rather than just mixing powders into a blend, materials break apart and recombine at a chemical level. By logging every exact measurement and repeating the steps until they yielded consistent results, Jabir proved that a raw material could be forced to become a completely new compound. The outputs of these controlled experiments were materials with properties that did not exist in the surrounding landscape. By refining raw metal ores, Jabir was able to burn away the structural weaknesses. The resulting purified metals were superior, allowing for the casting of stronger tools, more reliable coins, and accurate scientific instruments. Common, colorless salts were chemically altered to produce bright, concentrated textile dyes that locked into fabrics and resisted fading. His processes improved the clarity and strength of manufactured glass, while isolating specific chemical compounds provided purified ingredients for early pharmaceutical treatments. None of these properties existed in the dirt, the salt, or the raw ore. Manipulating the chemical structure of unremarkable starting materials was the only way to extract them. Before this period, investigations into nature relied heavily on philosophical speculation. Jabir replaced that guesswork with a system of physical testing and documented evidence. This shift turned chemistry into a discipline of creation. Researchers could now intentionally engineer substances that nature hadn't provided. Every field of modern chemistry still relies on this exact sequence. You take raw inputs, place them in a controlled reaction, and harvest the modified output. This 1,000-year-old method of forcing chemical change continues to provide the essential materials required for modern hardware and industrial manufacturing. This chart shows the exponential growth in synthesized chemical compounds created globally over the last century. That spike represents the development of lightweight aerospace alloys, high-yield synthetic fertilizers, and complex pharmaceuticals. We still face a world full of natural limitations, from global food supply challenges to aggressive diseases. These modern synthetic materials solve those limitations on a scale previously impossible with raw natural materials. Mastering these chemical reactions gives us the tools to design the world at a molecular level, building the specific substances required to meet the needs of future generations.